All right, so everybody, this is a pretty common set of questions that IB likes to ask about benzene. And so as you're going through these, it's going to definitely be stuff that we've talked about in class, but you're going to have to be able to use the right terminology. And so that's why I'm going to refer us directly to the question mark scheme that I have for this. And so the first question says, discuss the physical evidence for the structure of benzene, and then state the typical reactions that benzene and cyclohexene undergo with bromine. Okay, so for the first one, A, it is a 2-mark question. So you need any two of the things that are listed. So one thing we have not learned about is X-rays yet. But you can discuss that it makes a planar molecule. In other words, trigonal planar is the shape around each of the carbons. Or you could say that the carbon-to-carbon bond lengths are all equal. You could also say the carbon-to-carbon bonds are intermediate in length between single bonds and double bonds. Or you could say they all carbon-to-carbon-to-carbon bond angles are equal to each other. There is a note at the bottom that does say that you could also mention that all of the bond enthalpies are exactly the same as each other. Carbon-to-carbon bond enthalpies are the same as each other. Okay, so the next question is, what type of reaction does benzene undergo? And as we have learned, this is a substitution reaction, and that is different than a cyclohexene, which just has a double bond, not a resonance hybrid structure. So cyclohexene can undergo an addition reaction, and you only needed one for each of those, but you did have to answer for both there. Then the next question is, state the reagents used to convert benzene to nitrobenzene? That is in that first step that we talked about there. So the reagents needed were nitric and sulfuric acid. IB says concentrated, but we did not see that in our notes, so it is just fine if you write nitric and sulfuric acids. Basically, it says plus nitronium, excuse me. I'm looking at the question wondering, oh, it says, and the formula of the electrophile formed. Okay, I didn't realize that said that on there. So you did need to get the 2 marks. You needed both nitric and sulfuric acids and the nitronium ion. So there's that. Okay, so the next part asks you to go through the mechanism of the change, or the formation of nitrobenzene, and then second, the reformation of the, I guess, is the 2 steps leading to the addition of the nitronium molecule to the benzene, and then the reformation of the resonance structure. So the points that they give are the curly arrow going from the benzene ring to the N of the NO2 plus, and then the formation of that carbocation with the correct formula and positive charge in the ring. And then the third mark is a curly arrow going from the C to H bond to the benzene ring, so inside again, and then the formation of the organic compound, then the benzene, nitrobenzene, and the product of the hydrogen plus being broken off. Okay, so then it gets into a little bit of accepting the mechanism with corresponding Kekulé structures. In other words, if you drew the opposites with the double bond and single bond interlacing, that would be fine. Do not accept a circle in the M2 or M3. So in this step here or this step here, if you have a full circle, you do not get those credits. Accept first arrow starting either inside the circle or on the circle. So if this first arrow was actually directly on the circle, that would be okay. And M2 may be awarded for the correct diagram from the correct diagram for M3. And then it does say, showing the equation, so C6H5N2 plus H2SO4 if HSO4 is used in M3. Okay, so you're not likely to do that because we talked about it just as the breaking off of the H plus. And I know that there's more to this, but we have not discussed that portion of things, and you are not responsible for that. Okay, so the next problem we have is this stereochemistry quiz for practice. And the first one says an unknown sample is tested with a polarimeter for optical activities. The results of the test required no movement of the analyzers, what samples would give this result? If you had a pure enantiomer, we get to cross that one off because that one would actually give us a rotation. If we had an achiral compound, that's one of the examples that would give us a result of no movement. So B is a possible correct answer. A racemic mixture would also give us the possibility of no movement because remember, a racemic mixture is half of one enantiomer and half of the other enantiomer, and therefore they cancel the movement out in either direction. So that means D is our correct answer here. And then number 2, which of the following statements about enantiomers is correct? They have the same melting and boiling points. Yes, they have the same physical properties. That's why it's so hard to extract them from each other. The mirror image of the R isomer is the S isomer. Yes, that is also correct. They are mirror images of each other. The specific rotation of each stereoisomer has the same magnitude. Yes, just in the opposite direction. Without exception, the R stereoisomers will rotate light to the right. Not true. This is our one false statement. R simply means that the formation or the order of connectivity within the molecule is in the clockwise direction. It does not say, it does not speak to how the rotation of the light is going to occur. Okay, the next problem, which of the molecules below is a stereogenic carbon atom? So we're looking for a stereogenic carbon atom, and we can't do number 1 because when we do number 1, we're going to end up with an H down at the bottom, but that means we're going to have 2 CH3. So number 1 won't work. So that means we get to cross off A and we get to cross off E. All right, so then we get to look at number 2. Number 2 has 1, 2, definitely 3. I'm looking at it. Looking at it. Nope. This is nope. Because we end up with 2 things attached that are the same. So 2 is out. Okay, so that leaves D out, and that means C is our correct answer. And I have 1, 2. I'm going to have to draw some things out. Okay, let's go back to number 2. I have a, let me erase some here. We've decided that number 1 will not work because we have a carbon with an OH here and an H here and a CH3 here, and that leaves a CH3 here. That's why number 1 will not work. And so let's go look at number 2. In number 2, we have number 2 might work. We have a carbon with a bromine here, and we have a CH3 here, and we have an H here, and then the rest of it is CH, CH3, CH3. Okay, so number 2 is going to work. We've already been able to cancel out A and E because number 1 won't work, but number 2 is working fine for us. Now we just have to go ahead and draw out number 3 and see what we have. Number 3 has 1. So number 3, I can tell by looking at it that if it's this carbon if it is this carbon right here in the center, then these 2 groups are the same as each other. So it can't be that carbon in the center there. But what if it's this carbon here? If it's that carbon there, then we still have 2 CH3 groups attached. So it can't be number 3, which gives us only B for a correct answer there. Okay, so we are going on to the next problem, which is the Fisher projection formula for S-lactic acid, which is 2-hydroxypropanoic acid is. Oh boy. Okay, so we need to see if we can figure out 2-hydroxypropanoic acid. So this is referring to the fact that we have a 3 carbon. Let's go ahead and draw it out. Propan means I have 3 carbons. And propanoic acid, without me saying what the carbon on ethanoic and propanoic are always has at its end the carboxylic acid. So that's what's at the end. And this has the hydroxy, which is that OH molecule, leading us to have an H here and a CH3 here. Okay, so that's our format there. So we need to be able to make sure we get the S one. So the one I drew right here is let me just look here. I'm going to have, this is my number 1, this is going to be my number 2, and this is going to be my number 3. So this is actually my R format. So I can cross off anything that looks like that. Let me go ahead and go through here. So here I have my 1, my 2, and my 3. That is clockwise, so that's not good. And then I have my 1, my 2, and my 3, still clockwise. And then I have my 1, my 2, and my 3. There's my S. There's my counterclockwise. C is going to be my correct answer. Just let's go through the others. I have my 1, I have my 2, and I have my 3. Uh-oh, that's counterclockwise also. And then on this one I have, and that means I'm going to have to check my work. And then I have 1, 2, 3. So right now it looks like I can leave off E. E is out, and B is out, and A is out. So that leaves us 1, 2, and 3. So let's see here. 1, 2, 3. That's counterclockwise, and 1, 2, 3. That's counterclockwise as well. It looks like I got C and D. And I'm going to leave it for our conversation in class to see if anybody else agrees with me or they've got a reason why 1 would be a better answer. Okay, so let's look at some definitions. Isomers, which can be interconverted by rotation about single bonds. So these are going to be conformers. They can be conformed or sometimes they get called rotamers. But this means that number two is going to be A. B, isomers which have non-superimposable mirror images. That is stereoisomers. That's going to be a number 1. Isomers which can be converted only by breaking and remaking covalent bonds. And these are going to be, I'm looking at configurational isomers, chiral, achiral, stereogenic center. I think we're going to be talking about configuration isomers here. And then D, isomers which have the same order and attachments of atoms but different types of handedness and mirror images. So those are also enantiomers, so that is D. Did anybody choose being able to switch B and D with each other? And that might be a good choice there. Molecules which do not possess the property of handedness, they have a plane of symmetry, and they are identical basically. And so that would be number 5. And then a carbon with 4 different groups attached to it, that is chiral. Stereoisomers which are not mirror images have the same configuration at one or more centers but differ at the other centers. That makes me same configuration but differ at the other center. So that might be a diastereomer. Right, a substance which rotates the plane of polarization, allowing light to pass through, that is optically active. A substance which does not allow light to pass through, that is optically inactive. And I think we have covered all of them. I expect us to have lively conversation about this, and we will go on from there. Okay, hi everybody. I think that we need to go ahead and take a look at these questions. Which can show optical activity? This is our first question. I really think that what we're going to find here with this is that we're going to have to draw everything out. So we are looking for the one with a chiral center. So I have a C, H, Br, and then I have a C, H, and a Cl. And that is telling me that I have a double bond there. So A cannot be it. It has to have 4 things bonded to the center. B, I've got a CH, Br, and then so my H is going to be up here, and my Br is going to be down here. And that means I'm going to have these 2 things on either side. So let me get rid of all that mess. And that one is not going to be ours because basically this CH3CH2 and this C2CH3 are the same thing. So B's out. Then the next thing I have is C, Br, Cl, and then 2 CH3s. And the fact that I have 2 CH3s attached to that C means nope, that one's done. And so then let's take a look at our final one where we have a CH3, CH2, C, CH3Br. So what I basically have is a CH3, CH2, and then I have a C with an H bonded to it and a CH3 bonded to it and a Br bonded to it. And that's my one that has that chiral center, and that's the one that's going to have optical activity. Okay, so we're going to move on to this next one. Xylene is a derivative of benzene. One isomer is 1,4-dimethylbenzene. So there's that. Draw the structure of one other isomer of xylene, which retains the benzene ring. So basically, since this is the P designation, you can pick the M designation or the O designation, and that would be what you need. So we can go ahead and draw that in. So draw my, and then I would have CH3 here, and instead of putting it down here, I would put it over to the side. So there's my M designation, and that would be the structure of one other isomers. Okay, so write the equation for the production of the active nitrating agent from concentrated sulfuric and concentrated sulfuric and nitrated sulfuric and nitrate. I can't read. Write the equation for the production of the active nitrating agent. Equation for the production of the active nitrating agent from the concentrated sulfuric and nitric acids. So we have to. Okay, to best answer that question for the nitration, the formation of the nitronium ion is basically what it was asking for. So you could either show it as HNO3 reacting with H2SO4 to produce the nitronium ion and the 2HSO4 1- and H3O1+. That is one way of doing it. Notice that they also say that you can do this as well. This asked for the equation. This question did not ask for the mechanism. So what do we do if it asks for the mechanism? And let me see if I can show you what that looks like. If it said in its question the mechanism, then they're asking for you to show this portion of things where the benzene breaks its resonance structure and then remakes its resonance structure. All it basically asked for was this, or you could have written it out as this. Either one of those two would have been acceptable. Okay, so that literally means on the very next one that you needed to be able to explain the mechanism using all the curly arrows. So back to this, it is specifically talking about this portion of things with the arrows coming out of the benzene and then back into the benzene and the break off of the hydrogen ion and the formation of the nitrobenzene. So they would have given what basically they're looking at is point number one. There is point number one, the formation of the carbocation. That's another point. The reintroduction of the electrons from the hydrogen back into the benzene. That is another point. And then for the fourth point, the final products there. And that's the way they would be going to grade that one. Okay. Back to our question. Let me get rid of this. Okay, so bromine reacts with alkanes. Identify the initiation step of the reaction and its condition. Bromine reacts with alkanes. Uh-oh, I'm talking about review stuff, aren't I? So here we go, the initiation step. Oh, go back to what is the initiation step. They use that terminology on purpose because they want you to remember that Br2 has to have some UV light to break it up into two Br radicals. Okay, so then we have next 1,4-dimethylbenzene reacts as a substituted alkane. Draw the structures of the two products of the overall reaction when one molecule of bromine reacts with one molecule of 1,4-dimethylbenzene. Okay, so if what we've basically done is we have weakened the resonance structure when we have this 1,4-dimethylbenzene acting as a substituted alkane. So we're going to draw the structures of the two products of the overall reaction when one molecule of bromine reacts with one molecule of 1,4-dimethylbenzene. So the two products possibly would be, basically it's, oh, well, let's add one bromine in place of one of the methanes, and then let's add both bromines in place of the methanes. So you would end up with this, with one bromine and one methane still being on it. That would be one. And then the other one where you would end up with two bromines already attached. So in no way are we actually going to be messing around with the resonance structure here. We are just going to be breaking off the substituent groups. It's already substituted, and we're going to be putting on the bromine in this reaction, because this little bond right here, let me change my color, this little bond right here means that what we have is a single bonded alkane, and it is no longer, it is in addition to the resonance structure, but it's on the outside of it, and so we don't have to follow those rules. Okay, we are going to continue this on here. All right. The organic product is not optically active. Discuss whether or not the organic product is a racemic mixture. Okay, so let's go back to reminding ourselves what we have here. Do we have an organic product that is not optically active? And so we have to think about what is going on here. And let's just remind you that what we really have at any given moment is we have a double bond there and a single bond here, and we really just have a trigonal planar format. We still have that trigonal planar format. So we have a carbon that does have another carbon attached to it, but since it's a trigonal planar format, this is not going to be an optically active molecule. That means that there is no chiral center. There will be no chiral center. And as a result, this is not going to form two enantiomers. In fact, what we are going to have instead, there is no enantiomer. There is no chiral center, so no enantiomers. Okay, so that's why this is not a racemic mixture, because remember, racemic mixtures are an equal mixture of two different enantiomers, and you do not have two different enantiomers of the same thing. Okay, because you don't have four things bonded to a central carbon. Okay, number 3. What is the number of optical isomers of isoleucine? Okay, so that means we have to find out what is the number of chiral centers. Okay, because there would be 2 optical isomers if we have 1 chiral center, but there would be 3 or 4 optical isomers if we have two centers, and so forth. So let's see if we can identify what is going on here. So here I have a carbon with 3 things attached, so that is not a chiral center, but this one does have a hydrogen here, so that means that this one, there is one of our chiral centers right there, and this one does have a hydrogen here, and that makes this one of our other chiral centers, and this next one has 2 hydrogens attached, so it does not have, so we have a total of 4 optical isomers, 4 optical isomers of isoleucine. Okay, 2 from this carbon right here, and so 2 here and 2 here, so we would end up with 4 right there for our correct answer. Okay, we are going to go on here. The reactivity of organic compounds depends on the nature and positions of their functional groups. The structural formulas of 2 organic compounds are shown below. Deduce, giving a reason, which of the 2 compounds can show optical activity. So that means that we are looking for the one that has a chiral center. And so we are looking for 4 different things. And here is my 4 different things right here. So A can show optical activity, and I'm going to write it all out, can show optical activity because it has a chiral carbon. Okay, that means that it has a superimposable enantiomer, and it can rotate the plane of polarized light. Okay, so then it wants to draw 3-dimensional representations of the 2 enantiomers that A could be. Okay, in other words, A forms two enantiomers. Okay, so we need to draw three-dimensional representations. In other words, make your life easy and draw them as mirror images of each other. So we need to draw them out as mirror images of each other. So here we go. Let's go ahead and do that. So I have a carbon, and let's draw it out. I want to make sure I have that there so I can see it. I have a carbon with a COOH at the top, and I have, it has a CH3 2 there. It has a OH here, and it has a H here. Okay, so there's my mirror image that I'm going to do. So I'm going to have my carbon with the COOH here, and it is going to have on this side CH, whoops, okay, hold on everybody, gotta CH parentheses CH3 2, there's that first part, and then I have the OH, and then in the back I have the H, and those are going to be your three-dimensional representations. Okay, we'll get rid of that. And then state the reagents used in the nitration of benzene. Look, they repeat themselves. So we learned already that those two reagents are nitric and sulfuric acid. You can also write them out as their formula of nitric acid and sulfuric acid, just like that. So stating the reagents is all that is asking you to do. And then it's asking you once again to state the equation for the formation of NH or N2O. So we have here, if I can make my computer work correctly, so it simply wants the equation. It's not asking for you to determine any of the curly arrows or anything like that. Okay, so as long as you can write out the equation, I do want to stop and make sure that I have actually balanced this thing out. SO4 is good to go. NO2 plus and SO4 minus cancel each other out. I have three H's, one N, one S. Yep, it looks like everything is balanced. The next question, a polarimeter can be used to determine the optical rotation of an optically active substance. Describe what happens to plain polarized light when it passes a solution of an optically active compound. Simply put, it rotates the plane of polarized light. Okay, in one direction or another. Okay, easy enough. That's what it does, and that's going to be our result. Okay. A mixture of enantiomers shows the optical rotation. Suggest a conclusion you can draw from this data. Okay, so if a mixture of enantiomers shows the optical rotation, we have one mark here. You can answer one of these followings. They are not enantiomers of each other. Or you could say that they are not an equal mixture. Those are one of the two things that you might be able to answer there. Okay, I expect a lot of questions when we get into class. Hopefully you've been able to get through this.